Hello, students. Uh, welcome back to the new topic, new lecture. Um, Before that, we have discussed about the logic in the chapter number 1. We discussed about the propositional logic and the more extensive logic with the first order logic, or we call it the predicate logic, right? So we have a very good background now to translate the statements, English statements into, or mathematical statements into the logical expressions, and logical expressions to back into the English language, right? So now we will move forward to the second important chapter of our course, that is the basic structures, right? This course is about the discrete mathematics, sometimes referred as discrete structures in computer science. So we will be looking forward to the discrete structure, right? So what are the discrete structures available? So in this chapter, that is chapter number 2 of your book, we will be discussing about sets. We're discussing about the functions, sequences, sums, and matrices, right? So in this video, I will focus myself only on the sets. So in the upcoming videos, we will be discussing more discrete structures, right? So this is a chapter summary. So first of all, in this video, we will be discussing about sets and the set theory. That is one of the fundamental theory for computer science major. Then we will discuss functions and all of the related things, right? So sets. What is a set and what we are going to study? This is a summary of today's lecture. We will be defining the sets, definitions of the set. We will describe the sets using two methods. One is the roster method, another one is the set builder notations. And then we will see some important sets in mathematics. Then we'll talk about empty set and the universal sets, subsets and the set equality, cardinality, tuples, Cartesian product, and some other operations on the sets as well, like union, intersection, and all these things in this lecture, right? So what is a set? So sets are one of the basic building blocks for the types of objects considered in discrete mathematics, right? So what do we mean by the block of, okay, basic building block for the types of objects? So it means it deals with the objects. So what does that mean? It is important for counting. If we are going to count something, so set are the basic building blocks for counting. Programming languages have set operations. So most of the programming, in fact all the programming languages, they implement this set theory for the programming functions, right? If we talk about C language, Java language, then we talk about the compiler. So they all use this set theory as the benchmark in order to define the programming languages. Like for example, set of the keywords, right? Set of the keywords. So what are the reserved words or the keywords in a particular programming language, right? Similarly, set of the allowed variable names, right? So that's how the set theory is implemented in computer science, and this is one of the fundamental theory. So in later coming semesters, you will learn one subject, that is the theory of programming languages. So that theory of programming languages is based on the set theory, right? So set theory is an important branch of the mathematics. So many different systems of axioms uh, have been used to develop set theory. So many systems axioms are used to build this, to develop this set theory. Here we are not concerned with a formal set of axioms for set theory. Instead, we will use what is called naive set theory. So our purpose here in this course is not to prove the axioms of the set theory, right? We will just use naive set theory. What is that? We'll for sure discussing all these concepts in today's lecture, right? So what is the set actually? The definition of the set. A set is an unordered collection of objects. So it's a collection of objects, right? And the important thing is it is unordered, right? And one more thing, if you can add here, is is an unordered distinct collection of objects. So the objects are unordered, means the order does not matter. What object you place first, what object you place later, no problem. Distinct means, so one object is present one time only. The presence of the object is once only in a set, right? And this is the a set is an unordered distinct collection of objects. So for example, the students in this class is the set of the students in the class is a unordered set. So it doesn't matter you place what student at what number, no matters, right? And one student, uh, I mean, in one class there is only one student at one time. I mean, no student has its own copy, right? So similarly, the chairs in this room. So I mean, this is another example of the set of chairs in this room. So the object is a set. The objects in a set are called the elements. So whatever the objects are in the set, we call them the elements or members of the set, right? Set member or set element. A set is said to contain its element. So a set contains elements or the members, right? So the object, for example, the set of students in the class. So students are the set members, whereas class is the set, name of the set. So the notation, a belongs to a small a, that is the element. Small alphabet always represent the element of the set, and capital alphabet we use to represent the set name of the set. So small a belongs to a denotes that a is an element of the set A, right? If a is not a member of this set A, we write a does not belong to A, right? So that's how we define the sets. So describing a set using a roster method, as I told earlier that we have two methods to define a set. One is the roster method, another one is the set builder notation. So what is this? What is the roster method? This one. I mean, set S equal to, and we list all the elements of the set, members of the set, in a curly bracket, right? So A, B, C, D, these are the members of the set, and we place them in a curly bracket and we call it the set. So order is not important in the set, as I told earlier. A, B, C, D, B, C, A, D, or whatever other method, other order you will follow. So the answer remains same. So all are the members or the elements of this set S. Each distinct object is either a member or not, right? So listing more than once does not change the set. As I told you earlier, it's a distinct collection of the objects. So like S is equal to A, B, C, D. This is a set. So it doesn't matter if you write B multiple time or C multiple time. No problem at all. So it's still, it will be counted simple. I mean, it will be counted once for the set. So this is equivalent to this one, right? So we do not write the same object multiple times in one set. Ellipses, these three dots, right, may be used to describe a set without listing all the members when the pattern is clear. For example, set of all small alphabets A, B, C, D. Rather than writing the 26 entries, we can just write A, B, C, D and then dot 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 comma Z. So that means starting from A to Z, these all are the member of this set S. So for example, set of first 10 positive integers, right? So or greater than 0. So you can just write A is a set, and then you can write 1, 2, 3, dot dot 10, right? So when the pattern is clear, you can write using these ellipses. Clear? Okay. So using the roster method, few examples are there. Set of vowels in the English alphabet, right? So you can write B equal to A, E, I, O, U. So directly you can list the elements of those sets in the set, right? So set of all odd positive integers less than 10, right? So 1, 3, 5, 7, 9. O, set O contains the element of all odd positive integers. So set of all positive integers less than 100, right? So 1, 2, 3 up to 99, right? So this is the set, another set example using the roster method, but we are describing the set. Set of all integers less than 0. So that means starting from, we don't know from where, infinite until -1, right? So So that's the set of all negative, all integers less than 0 means negative integers, right? So some important sets are there. I mean, we must memorize them. We must understand them. Capital N is used to set the number of natural numbers. And what are the natural numbers? Is starting from 0 until infinity. All the positive integers including 0 are called the natural numbers, right? So capital N is used to represent set of all positive integers. Clear? The capital Z is used to represent set of all integers, all positive integers, all negative integers, right? So starting from the infinity, right, dot dot dot, it's continuous from -3, -2, -1, 0, 1, 2, 3, and so on. So this is the set of the integers represented with Z. Z plus, right, Z plus is the symbol to represent the positive integers. So means starting from 1, 2, 3, and so on. These all are the positive integers. R R symbol is used to set for the set of real numbers. What are the real numbers? Real numbers, we know that it's collection of the rational number as well as the irrational number. All the fractions, all the integers, whole numbers, natural numbers, all come in the real number, right? So a set of all real number is represented using R. R plus set of positive real number, right? So it's similar to the Z plus. So all the positive real numbers are represented using the cap R plus symbol. C is the set of all complex numbers, right? All the complex numbers are represented using C, capital C. Q, set of all rational numbers, right? So all the rational numbers are set of all the rational number are represented using the symbol Q, right? Similarly, we have Z minus, right? So you can understand if Z plus is representing the positive integer, Z minus is representing the negative integers, set of all negative integers. Similarly, we have R plus, we have R negative, right? So R negative is set of all negative real numbers, right? So these are some important sets in mathematics that we will use, that are being used widely in computer science and in mathematics. So you must know, you must be clear what these symbols mean and what this symbol actually represents, right? So now let's see another method for describing the set, that is a set builder notation. So set builder notation is, we will be mostly using this set builder notation in throughout this course. So it specifies the property or properties that all members must satisfy. For example, S is a set. I mean, this is the way to describe the set, not having all, not listing all the members of the set. Rather, we actually give the description. So for example, S is the set of all members X such that X is a positive integer less than 100. So this is similar to the S equal to 1, 2, 3 up to 100. Oh, sorry, less than 100. So it's 99, right? Is that clear? So this is how we write it and how we read it. S is a set, S is equal to X such that X is positive integer less than 100. Similarly, O is equal to X such that X is an odd positive integer less than 10, right? So that means it contains the element from 1 to 9, that is all positive odd integers, right? Similarly, O is another set X, all the elements X belongs to Z positive, right? Such that X is odd and X less than 10, right? So that means positive integers, right? So X is odd and X is less than 10. This is another way to write this. These two are same, right? So this and this are, these two definitions are same, right? So this is how we actually use the set builder notation to represent the sets, right? So predicate may be used as well with the set notation, in the set builder notation. Instead of writing this whole sentence, we can use the predicate. How? S is equal to X such that P of X, and then we have to say what does this p of x means. Like say for an example, s is equal to x such that prime of x. What does that mean? Set of all prime numbers, right? So this is equivalent to, if we write x such that x is the member of all prime numbers. So positive rational numbers, for example, q plus, the definition is x belongs to R, it belongs to the real numbers, such that x is equal to p divided by q for some positive integers p and q. That is the definition of this q plus, right? Okay. Interval notation. So this is another notation to describe the sets that we use with the set builder notation, right? So as for example, understand these two things. One is the inclusiveness, another one is the exclusiveness. What do we mean by the inclusiveness and exclusiveness? Means, so if this is the scenario, see, these are the closed intervals. For the closed intervals we use these brackets. For the open interval we use these brackets, right? Curly brackets. Okay. um, so if there are square brackets, we use that, we say that these are the closed intervals. Means x such that x is greater than or equal to a including a, and x is less than or equal to b. So a and b both are the members of the set, and x is defined as x is between a and b, right? So let's say one more example. So here you can see a comma b, but the bracket is different. We use this square bracket with a and this round bracket with b. So what does this mean? X such that x is greater than or equal to a, this a is included because this is closed interval, and x is less than b, not less than or equal to b. Less than b means b is excluded, b is not part of this set, b element is not part of this set, right? Similarly, here you can see the round bracket a, that means a is not part of the set, and the square bracket with b, that means this b is element of this x. So we can say x such that x is greater than a. Now a is not included, and x is less than or equal to b, right? So if this is a scenario a comma b with open with the square bracket with the open interval, so simply x is the element of the set such that x is greater than a and x is less than b. That's how we actually define the interval notations. So remember, two interval notations we have. One is the closed interval, another one is the open interval, right? Okay. Next, universal set and empty set. What is the universal set? The universal set that is represented with capital U is the set containing everything currently under consideration. For example, set of students, for example, set of patients, for example, set of chairs. So all things that is considered, set of flowers, right? So there are several types of the flowers, but I'm saying set of flowers that includes all the types of the flowers as well. So U is the set containing everything currently under consideration, right? So sometimes it is implicit and sometimes it is explicitly stated. So sometimes we implicitly state it, sometimes we explicitly state it. So the content depends on the context, that what context we are using, right? So for example, I gave you the example set of the flowers. So that also include the set of roses, that also includes set of jasmine and all the type of the flowers, right? So it totally depends, the content of the set depend on the context, or at what context we are talking about. We'll be seeing many examples later in this lecture about the universal set. Okay, here we can also represent the set with the help of a Venn diagram. Venn diagram is the graphical representation of the set given by the John Venn, right? So this Venn diagram is named after his name. So say for example, the set universal set U is the set of all alphabets, set of all alphabets, English alphabets, right? And V is the set inside this set, universal set, that is set of vowels, right? So U contains from all the elements A, B up to Z, and among this set, universal set, we have a set V, that is the set of vowels. So universal set for vowel set is the set of alphabets, right? So the empty set is the set with no elements at all, right? So if we say empty set means the set does not contain any element, right? So the symbols used for the empty set is this phi sign, right? And sometimes we simply use these curly brackets without indicating any of the uh, element inside. But remember, these two things are different, right? This phi sign represents the empty set, and this is different, and this also represents the empty set, but then this does not represent the empty set, right? This means the set that contains an empty set, right? So the definition is different. This is different than the above two symbols, right? So Russell's paradox is also helpful in order to understand the set theory, and it says let S be the set of all sets, right? It says let S be the set of all sets which are not member of themselves, right? Which are not member of themselves. A paradox results from trying to answer is the question, is S a member of itself or not? Since S is the set of all the sets, all sets that are not member of themselves, right? So then what about S? Is S a member of itself or not? So that's a paradox. This was actually this was I mean this paradox was uh, given by this the scientist mathematician, that is the Russell, and this was basically from the there is another related paradox, that is Henry is a barber who shaves all people who do not shave themselves. A paradox results from trying to answer the question is, does Henry shave himself? So that's again another thing. So this was the foundation for the fuzzy set theory. Fuzzy set theory. So what is the fuzzy set and what is the fuzzy set theory? This is beyond the scope of this lecture. This might be we will be discussing later on in some classes, maybe like the artificial intelligence class. So I mean, but the set theory is again used there to answer such type of the questions. So some things to remember. Set can be element of another set. So rather than having the elements, individual elements, we can have the complete set as an element, right? So like this is a set, this single element, this is another set. So this combined can be can represent a set as well. So set of this is a set containing N, Z, Q, R. We already know what are these symbols. They N also is a set of natural numbers. Z is a set of the integers. So R is the set of the rational number. Q is the set of the complex numbers. So these all are the sets. They are element of this set as well, right? So the empty set is different from a set containing the empty set. This I already explained you in the previous slide. So this is different than the empty set. Clear? So now let's talk about the set equality. So when we call two sets are equal, so two sets are equal if and only if they have the same elements. So two sets said to be the equal if both have the same elements in them. So therefore, if A and B are sets, then A and B are equal if and only if this is true. That what is that? For all x, x belong to A, X belong to B, and the relationship is the bidirectional, right? So you know bidirectional from the prepositional logic, you know this for all from the predicate logic. So this is the definition of the set equality. Means if A and B are sets, A and B are two sets, then A and B are equal if and only if for all x, x is the member of A is bidirectional with the x is the member of B. We write A equal to B if A and B are equal sets. So simply if both are equal, we can use A equal to B. Right. So here are some examples. So there is one set 135 and there is another set 351. So these two are equal. So order does not matter, but the members are same. The elements are same. So these two sets are equal. 1 5 5 5 3 3 1 and 135. These two sets are equal. Why? Because all the elements in set A, let's say this is set A, this is set B, all the elements in set A are also member of the set B. So we do not write the repetitive elements in one set. We already discussed this. So these two are the same sets. So from this definition, you can see X is member of A. For example, 1 is member of A. Yes. X is member of B. 1 is also member of B. And this is bidirectionally true. So this is true for all the X elements. So then we call A is equal to B. A and B are equal sets. Subset. What is a subset? The set A is a subset of B if and only if every element of A is also an element of B. Now this is different than the set equality. There, the member of the sets must be same. But here what we say, it's not necessary. So for example, if you have a set A with 1, 2, 3, 4, 5, and you have a set B with elements 1, 2, 3, 4, 5, 6 up to 10, right? So if I say set A is the subset of set B, what does it mean? All the members of the set A must be present in set B. Then only if I can say set A is the subset of B. And there may be some other members of in set B as well, right? So set A is a subset of B if and only if every element of A is also an element of B. The notation to represent the subset is this one, right? So we say that A is the subset of B, is used to indicate that A is a subset of set B. So if A is the subset of B, holds if and only if this condition is, this is true only when this statement is true. For all X, X is the member of A implies that X is the member of B, right? So for all the X element, X should be member of A implies that X is the member of B. In equality, we were having bidirectional. In subset, we have the implication, right? So because A is also an element of empty set is always false, right? So for in an empty set there is not a single element, so A belongs to empty set is always false. So that's why we can say that empty set is the subset of S. So actually empty set is the subset of every set, right? So every set, every possible set. So empty set is the subset of every possible set. So because A is the member of S implies that A is the member of S. So S is subset of S itself. So every set is a subset of itself as well. So remember two things now. One is empty set is the subset of every set. Every set is the subset of itself as well, right? Okay. So showing that A is a subset of B, to show that A is a subset of B, show that if X belongs to A, then X also belongs to B. So you can represent, if we ask you that, show that A is a subset of B, then how you are going to do for every member X, you will see if X belongs to A, then and that also belongs to B, then only you can prove that this is the member. I already have given you example here. So 1 is member in both. X is equal to 1. 1 is member of A, 1 is member of B. 2 is member of A, 2 is member of B. 3 is member of A, 3 is member of B. So all the elements are member of both A and B. Since we can prove that, we can show that this is the subset. So how to show that A is not a subset of B? To show that A is not a subset of B, and we use this symbol in order to represent the not a subset, right? So this is subset of B. In order to represent not a subset, we just mark this symbol. Find an element X belongs to A with X does not belong to B. So find any single element that is present in A but that is not present in B. So such an X is a counter example to the claim that X is member of A implies X is member of B. So that's why in this way you can show that this is not the subset of B. A is not subset of B. Here are some examples. The set of all computer science majors at your school is a subset of all students at your school. isn't it? So I mean, the set of all students in AUPP is the universal set, and in that a set of all the computer science major is another set. So computer science major is the subset of the students of AUPP. The set of integers with squares less than 100 is not a subset of the set of non-negative integers, isn't it? So set of integers with the square less than 100. So what are the set of integers that have the, for example, 2, 4, right? I mean 2, 3, 4, 5, 6, 7, 8. Many integers are there whose square root is less than 100. Whose square is less than 100, not the square root. Square is less than 100. But then the negative negative integers, they also have the same. So for example, the square of 3 is 9 and the square of negative 3 is also 9, right? So what does it mean? The set of integers with the square less than 100 is not a subset of non-negative integers, right? So it's not the subset of the non-negative integers, because it also contains the negative integers. All right. So another look at equality of the sets. So recall that two sets A and B are equal, denoted by A equal to B if and only if, right? This is the description. For all x, x belongs to A, bidirectional x belongs to B. So using logical equivalences, we can have that A equal to B if and only if. Now let's say the logical equivalences for this. So what we can say, this is another definition of the equality of the set. For all x such that x belongs to A implies that x belongs to B, and x belongs to B implies x belongs to A. So this is nothing but the definition of the bidirectional as well. So you can say you can always write either this, you can prove in this way, or you can prove the equality of two sets by using this definition as well. So this is equivalent to as well if A is a subset of B and B is also the subset of A. So I mean, if you can see, if two sets are equal, if A and B are equal, they are subset of both as well. So A is the subset of B and B is subset of A if two sets are equal. All right. Then a proper subset. What do we mean by the proper subset? If A is a subset of B, but A is not equal to B, right? If A is a subset of B, but A is not equal to B, then we say that A is a proper subset of B, and we denote it using this symbol, and we do not put a line under this this symbol, right? So A is a proper subset of B. If A is a proper subset of B, then this definition is true. So if you can see from this diagram, means A is a proper subset of B if all the elements of A are present in in the elements of B, and these two sets are not equal. Then we call it the proper subset, right? And the definition says, for all x, x belongs to A implies x belongs to B, and there exists some x such that x belongs to B and x does not belong to A. So x is member of B, but x is not member of A. That's why it is not equal. So that's called the proper subset. All right. Set cardinality. So cardinality refers to the counting the members in a set, counting the number of elements in a set. So if there are exactly n distinct element in set S, where n is a non-negative integer, we say that S is finite. So remember, set may be finite, set may be infinite. If there are the n elements, right, that you can count, then set is finite. And if the set elements cannot be counted, then the set is infinite. So cardinality refers to the finite set. We can always compute the cardinality of the finite sets. We cannot compute the cardinality of the infinite sets, right? So the definition is the cardinality of a finite set A, denoted by this symbol A with two bars, like sometimes you may call it mod symbol, but this is not mod, this is the cardinality. This is different than modulus, right? Is the number of distinct element of A, the number of elements in set A. So for example, the cardinality of empty set is 0. There is no element in this set. Let S be the letters of the English alphabets. Then cardinality of S is 26. Why? Because there are 26 alphabets in this English 26 elements in the English alphabet, right? So set 1, 2, 3. The cardinality of this set is 3. The cardinality of set containing the empty set is 1, because there is one element, that is emptiness, right? The set of integers is infinite, so we cannot compute the cardinality of the integer sets, right? The infinite sets, right? Power set. What is a power set? So the set of all subsets of a set A, all possible subsets of a set A, denoted by P of A, is called a power set of A, right? So let's, for an example, if A has two elements, A and B, then the power set is, remember, all the possible subsets. I told you in the previous slides that empty set, emptiness, or the empty set is the subset of every set. So empty set is there because this is the subset of all these I mean every set, so it is the subset. So the power set of A contains this set, all the elements A, B, and then combination of A and B. All right. So similarly, if I have a set, say for example A, and I have elements 1, 2, 3, and I have a set B with A, B, right? So what is the power set of A and B? Okay. Uh, what is the power set of just forget about B. What is the power set of A? So let's compute the power set of A. So power set of A is, first of all, the empty set, then all elements one by one, 1, 2, 3, in form of the set, right? Because power set is the subset, I mean possible, all possible subsets are in the power set of A, and then the combination of this 1, 2, 1, 3, right? And then 2, 3, and then 1, 2, 3, right? So 1, 2, 3, 4, 5, 6, 7, 8 elements, right? So if a set has n elements, then the cardinality of the power set is 2 power n. So if the set elements were 2, we were having 1, 2, 3, 4 power sets. But if the cardinality is of the set A is 3, we are having the 8 sets. So similarly, if we have if the cardinality of set A is n, set A is n, cardinality of set A is n, then the power set of A will be 2 to the power of n, right? That's it says here. And definitely we will be discussing this in more detail in upcoming chapters as well. So we'll see how to compute the power set in coming few minutes. So what is the tuple? Tuples. So the ordered n tuple, say for example A1, A2 up to AN, is the ordered collection that has A1 as its first element and A2 as its second element, and so on until AN. Remember here, this is the ordered tuple, right? The ordered does matter here now in tuple, right? So what happens? Two n tuples are equal if and only if their corresponding elements are equal, right? So say for example, we write the tuples in form of the ordered pair, like this one, A comma B, right? A comma B is one tuple, right? So 1 comma 2 is one tuple. This is the ordered pair. This is not equal to 2 comma 1. This is different, right? So this is different, this is different. Elements are same, but order does matter in tuples. So these are basically the ordered pairs. So two tuples are called equal, I mean two tuples are called ordered pair, right? So they are only equal if they both have the same value. A comma B is equal to A comma B only. It does not equal to B comma A. So the ordered pair A, B and C, D are equal if and only if A equal to C and B equal to D. If A and C are equal and B and D are equal, then only these two tuples are called equal, right? That these two pairs are called equal, ordered pair are called equal. All right. So let's talk about the Cartesian product now. What is the Cartesian product? So the Cartesian product of two sets, we represent it A cross B, right, is the set of ordered pairs AB where A belongs to A and B belongs to B. So basically two sets A and B, right? So this A belongs to A and B belongs to B, and the set of all ordered pairs, possible ordered pairs, are called the Cartesian product. So for example, A and B are two sets. A cross B then represents the result is A comma B, such that A is member of A and symbol is there, B is member of B. All right, so here are some examples. If the set A is AB and set B is 1 2 3, so what is A cross B? A cross B is all the possible ordered, all the set of n tuples of A and B. So what does that mean? First of all, we will use this A and 1, right? So A1, then A2, then A3, right? So the order does matter, right? A, that's the A cross B. So then after that, B, second element of this first set A, B1, B2 and B3, right? So this is A cross B. So remember, this is not A cross B is never equal to B cross A until or unless A and B represent the two similar to A and B are equal, right? So A cross B is not equal to B cross A. They both have the different. Similarly, for example, if you have B cross A, so B cross A means you will be let's compute the B cross A. Sorry, I don't know what is the mess with this pen. Okay, so B cross A, right? So B cross A is, now you have to take B first, 1 comma A, then 1 comma B, then 2 comma A, 2 comma B, and then 3 comma A and 3 comma B. So this is the result of B cross A. This is entirely different than the A cross B because this order does matter, right? So a subset R, one more definition of the relation here. A subset R of the Cartesian product A cross B, these ordered pairs, subset of these ordered pair, for example, these three, these two or these three, whatever, is called a relation from the set A to set B, right? So what is the definition of the relation? The Cartesian product A cross B set of the subset of A cross B is called a relation. So definitely we have a separate chapter on relation, but we will also discuss this relation in coming 1 or 2 lectures after the functions as well, right? But the relations, we have a separate chapter in chapter 9. We will be discussing this in detail in that chapter. So the Cartesian product is clear. Now let's move next. What is it? Okay. So the Cartesian product of sets, multiple sets, A1, A2, A3, A4 up to AN. So Cartesian product of set n sets denoted by A1 cross A2 cross A3 cross up to cross AN is the set of ordered n tuples, right? N tuples in a way A1, A2, A3 up to AN, where AI belongs to the AI for I equal to 1, 2, 3, 4 up to N. We can write mathematically A1 cross A2 cross A3 up to cross AN is a result of the ordered pair, such ordered pair, right? A1, A2 up to AN, such that this I represent this index 1, 2, 3, 4 belongs to A of I for I equal to 1, 2, 3, 4 up to N, right? So for example, what is A cross B cross C, where A is 0, 1, B is 1, 2, and C is 0, 1, 2. So we have three sets A, B, and C. So what is the A cross B cross C? So let's see. A cross B cross C is, first of all, you will take the element from A, that is 0, right? You are going to make an ordered pair 0, 1, 0, right? Then 0, 1, 1, right? Then 0, 1, 2, right? So you have consumed this 0, 1, 0, 0, 1, 1, 0, 1, 2, right? Then the second element 1, 1, oh, sorry, second 0 with the second element of B. First 0, 2, 0, right? 0, 2, 1, 0, 2, 2. All right. Then the next element from the first set, 1, 1, 0, 1, 1, 1, 1, 1, 2. All right. Then second element from the second element from the second set, 1, 2, 0, 1, 2, 1, 1, 2, 2. And you have now consumed all the elements from all three sets. So this is how we are going to form A cross B of the multiple sets, A cross B cross C, and there are 4 sets, 5 sets, 6 sets. Similarly, we can compute the Cartesian product for those products. Cartesian product is really, really important. It has um, very vast the applications in computer science that you will be counted throughout your computer science journey. So truth sets of the quantifiers. Given a predicate P and a domain D, we define the truth set of P to be the set of elements in D for which P of X is true. So the truth set of P of X is denoted by this way: X belongs to D such that P of X. So D represents the domain of the P of X. P of X is the propositional function. So here is one example, the truth set of P of X where the domain is the integer and P of X is X. Now this is the modulus. Mod of X is equal to 1. Then what are the possible values where mod of X becomes 1? It could be either -1 or the +1, right? So this is the set of this P of X, right? Set of this in domain, integer domain for the P of X. P of X represent the mod of X equal to 1. The possible values in the set is -1, 1. All right. Okay. So now we will talk about the set operations, but just wait for 1 second.